Hi, thanks for watching my video. I am Yuluo. My student number is 23156201. In this video, I will introduce the Evolutionary Algorithms Project with GP. I will introduce this project in 4 parts. Part 1, Introduction. Part 2, Preprocessing. Part 3, Function state. Part 4, Result and Conclusion. This project is a binary classification problem. Use the census income dataset to predict whether a person's income is greater than 50,000. The training dataset contains features of a person and whether his income is greater than 50,000. And the test dataset only contains features of a person. We need to train a classifier using the training datasets so that it performs well on the test datasets. I use genetic programming in this project. There are 11 features in the training dataset, 7 of which are nominal variables, 4 of which are numerical variables. Before training mode, these nominal variables need to be transformed into a form that the mode can understand. I use one-hot encoding and perform feature scaling on numerical variables. I get labels of income from training dataset. They are represented by 0 and 1. Next, I will introduce my function set. In this code, I use a one-hot encoding to transform nominal feature and perform feature scaling on numerical features. I create primitive set and add functions like add, subtract, sine, and cosine. Then I set up a code that generates random numbers. I create a toolbox, then register expert to use GP's function to generate individual, register individual to initialize an individual, register population to generate population, register compile to compile individual into program. This is my fitness function. I use compile to compile the individual, and use the compiled function to predict each sample of the training dataset. If the prediction is greater than 0, it is 1, else it is 0. I use accuracy score function to calculate accuracy, then return the accuracy. If there is an exception, return 0 accuracy. I register evaluate, select, mate, mutate function. I use tournament selection and one-point crossover. I set two mutate function for generating a new train expression and a uniform mutation. I create a statistic tool, including average, standard, deviation, minimal, and maximal. I run the GP mode. I use the mu plus lambda strategy, where mu is the size of current population, and lambda is the number of new individuals generated. I create graphs to analyze the data. Next, I will introduce the result and conclusion. The following parameters were used in the experiment. The maximal accuracy is 0.7880. The maximal fitness of the first generation is 0.6700 and reach the maximal fitness of 0.7880 in the 252 generation, after which there is no increase. From these two charts, the fitness rise in stepwise fission touch the maximal fitness around the 215 generation. The individual size increase with the increase of fitness. After 215 generation, the individual size increased significantly, but the fitness has not improved. The accuracy of the experiment is 0.7880, which proves that the mode performs well. There is no improvement for fitness after trying different parameter settings. This situation may be because of the limitation of the GP mode, and some people use GE to achieve higher accuracy. In this GP mode, setting a smaller population size and generating more times is more effective. It may be because the smaller population size make bigger difference between individuals in one generation, and generating more times ensure wider exploration. Thanks for watching my video.